We found if we solve these circuits, all first order circuits, answer is like approach. So we only have so is first order circuit only need to check three values. Which value? The response of circuit when a long time is passed from current state. The response of circuit at the moment of changing the state. Okay. And another one, what do we call top time constant? In RC circuit, it's very in RL circuit, what does Y means? What is Y? It can be voltage or current on every branch. Yeah. Every branch that we are in. All branches, voltage and current are. The behavior is exponential. What is the difference? Only the coefficient. Its value when time goes to infinity, the value when time changing, and the time constant is taking the whole circuit. In an RC circuit, when we are at the moment of changing the states, how a capacitor behaves when I'm changing the state. It's kind of voltage level. Why? Because capacitor voltage cannot jump, so capacitor tries to keep its voltage across its state. So we can consider a capacitor like when a long time is passed, capacitor is we can consider capacitor as a open. How about inductor? When we change the state, inductor tries to keep its current. Okay. When it tries to keep its current, that behaves like a current. Long time after the current state of the circuit, it becomes a short. Suppose I have this circuit. Suppose I have this circuit at the time of zero, the switch is gonna close. Okay. Okay. How we can find the voltage of the capacitor? That's first order circuit or second. That's first. Why? Because we have only one capacitor and all are the resistive level. For a long time, this switch was open. So the circuit was like before this switch. So the circuit was like that. You know, this circuit is in this state from minus infinity to when time goes to zero. That means the capacitor should be it should be charged or discharged to the value. Okay? We don't know how much of the value we will calculate it, but we know after a while capacitor should be how much is the voltage of the capacitor in this thing? 2 volt. Okay. If I write KVA, since this current is below the voltage across these two ohms below, so VP should be, which means we charge this capacitor to 2 volt. When we close the switch, what will happen? The voltage of capacitor can jump after changing. You know, 0 plus means after changing the state, 0 minus is before changing the state. Before the changing the state, we calculated the voltage of the capacitor is 2 volts. After closing the switch, do you think the voltage of capacitor can drop? Right? Yeah. Or impulse. Since we never push or force the capacitor voltage to drop, and there is no impulse current, the voltage of capacitor stays after changing. So now I want to write VTT because we when time goes with me. But you, I'm not sure you can see or not. But when T goes to infinity, what will happen? the amount of time you pass from this circuit. But the voltage of capacitor is gonna change. How much? You should be able to say that. A long time is passed, yeah, which means capacitor is like capacitor is like opposite. Yeah. So I can consider I want 0.33 infinity. How should I find it? Um, if I consider here graph, here I can consider V infinity. How much is here? How much? But we can easily write it. You can do that. Perhaps how much is this voltage? I consider here how much is voltage of this node? Oh, you cannot see here. Oh, here. Yeah, easy. I thought that's it. 2 volt. I write 1 kVA. This current is minus 2 volt over 4. The this current V minus 0 over 1. And this current is coming inside minus 1 equals to. So I have V V. That means I can, and I have this one. Zero. I want you to find. I, I only need to find the equivalent from perspective of capacity. How much is the capacitor, the resistance that the capacitor is? Sorry, 2 over 3, which means 1 parallel to the 2 multiplied by 1. 8 So we found VC infinity plus VC. Maybe one. We don't need to write differential equation to solve for the but it has two conditions. You remember what was and what were the conditions? Yeah, exactly. The circuit should be first order. We should only have one capacitor or one inductor, and the second condition, we should only have constant independent sources. We cannot have AC independent. To use this relationship or this relationship. Any question on
Can you go down and take a picture?
that's a preview of the last session? Okay, now we want to start second order circuit. As you probably know, second order circuit is we have two elements that they can store energy, like two capacitors or two inductors or one capacitor, one. Like first order circuit, we can have zero input response, zero state response, and I will explain state space equations in chapter 8. And the complete response. There is zero input response is when I set all independent sources zero. Typically, zero input response, zero state response is obvious. What are the states? The initial condition. If I set all initial condition of initial voltage of capacitor or initial current of inductor. If I set them zero, which means I'm looking for zero state response and complete response, sum of these two. One of the most important is that you will see a lot in electronic, we call it RNC10. This is the RNC. We have one capacitor, one inductor, and one resistor. In fact, if you have one capacitor and one inductor in parallel, the whole other circuit you can find a Norton equivalent source. It doesn't matter what circuit these two are connected. You can find the equivalent of the other circuit and the node. Here we are looking for zero input response, so we set this current to zero. Okay, let's see how it's gonna be equation. If I write a KCL here, IC plus IC plus IL plus IR should be 0. If we write a KVL here, minus BC plus BL should be 0, which means B should be
Equal to.
equal to BL. And if I write another KVL here, minus BL plus BR should be 0, which means BL should be equal to 0. These three are in parallel, which means the voltage should be equal to each other. We know this from our parallel. How much is current available? Based on Ohm law, V equal to R. Relationship between current and voltage of the inductor, V L NDI over dt. And for capacitor, that IC equal to CdV over. We were supposed to memorize the equation. If I sub IC by CdV over dt, I have equal GVR at PA, GE 1 over that conductor. Plus I can rewrite VC and VR by VN, and we know VN is LDI over by sub VN in this equation. We will have the second of the differential equation with constant coefficient. That second order, we need to have two initial values. If we are looking for IN at the moment of 0 is I0, and we need this first order derivation, which is how we can find this. So this one we know, yeah. But how we can find the derivation of IN over IT?
What will the question be?
How can we find this value? Where this comes from? Exactly. Yeah. When we have a relationship between voltage and current of the element, we can apply it in all the time. Okay? When I apply this equation for the time of zero, I have E and L over denominator of V. So we know VL is equal to VC and VC0 V0. These two are initial conditions. Okay, I have a second order differential equation. If we solve this equation, how do we solve the second order differential equation? We need to find the characteristic equation. Do you remember you had differential equation? But the others should have. Yeah. You pass the differential equation course.
Yes.
And if we solve this characteristic equation, we will have three different responses. The first one, if S1 and S2 are real, then we have two different poles. We have two different poles. If they are the same, we will have only one pole. If they are imaginary, we will have different response that we are going to categorize the. So we summarize this equation with these two values. We call alpha as the damping factor and omega 0 as the resonation frequency. Frequency damping factor. It does mean we are dealing with this equation. If we solve this equation, we will have three different responses. The first one, S1 and S2, both are real. In the circuit, both of them should be real and negative. They cannot be positive. Because they should be kind of dynamic. Which means if t approaches to infinity, this value should go to 0. It cannot be increased. Unless we have positive feedback, we will see electronics. Okay, when S1 and S2 are real and negative, the response is like that. We call it overlap. Depends on K1 and K2, it's going to start from one point and it goes, it reaches to another point and stay there. After going, it's going to start from one point and goes to.
So what is K1 and K2? K1 and K2.
Their coefficient, we will find them based on the initial condition. Right now, we don't know the value. There are some variables that we will find them based on the initial value. The coefficient and variables. When S1 and S2 are equal, we call it critically damped circuit. Its response is something like that. It's a bit faster than overdamped. And when S1 and S2 are imaginary, we call it underdamped. It cannot move exactly there. a bit lower and going back, and after a while, it goes into zero.
The first drawing for the up or down doesn't touch the zero.
It reaches to zero.
So what's the difference between the up down?
These two.
Yeah, and the
And
graph.
this one it goes, all them will go to zero when it goes infinity, yeah, because of this step. All of them are gonna reach to zero.
What's the difference between the up or down and down?
The speed of them, yeah, this one is 5.
So only the speed is,
Yeah.
but the graph is the same.
Yeah, almost. So here we have the summary. If we have two real and negative code, we will have this kind of response. If it's critically down, which means S1 and S2 are equal, we will have these waveform. We can see these are look like each other. This one is a bit faster than that one. And under that, when we have a small resonate, but after a while it's gonna reach again to zero. We have a special case we call it lossless, which means when we alpha is zero. When alpha is zero, let's see what is alpha. This is alpha. When alpha is zero, when G is zero, that means conductance. Our conductance is zero, yeah, which means R should be infinity. Yeah. When alpha is zero, or which means the resistance is infinity, we have one lossless or undamped condition, which means if we have only one capacitor parallel to one inductor, what is gonna be the output? One sine or cosine. And we call it lossless or undamped, which means you can have only one DC input as initial condition, and your output would be a AC signal. Can we have it in a real book? If we connect one inductor and one capacitor, can we see waveform, the sine, cosine waveform? Right. If I connect one capacitor and one conductor in parallel and set the initial voltage of capacitor to 1, can I see this waveform? In a one circuit, one of them is giving another circuit, another. But can it last until infinity? Can I have a really pure sine waveform? But on the paper, it should be 8, but in reality, we exact. We have some parasitic resistance. Yeah. We have one parasitic resistant with capacitor and one with inductor. The parasitic resistance of inductor is not high, but I think it exists here. And after a while, it's gonna be kind of under damped circuit because there is a small alpha here. After a while, it's gonna go to 0.
Let me ask you a simple question. When is the capacitor giving energy? Because you just mentioned giving energy. When is the capacitor giving energy? So let's say, for example, we look at the voltage of the capacitor. If the voltage of the capacitor is coming down, is it giving energy, or is the voltage going up? It's and the structure gives energy when its current is going down. No. It's a simple physics. So basically, as the current goes up, inductor stores it. Comes down. Capacitor, when the voltage comes down, if the voltage goes up, stores it. But the capacitor and inductor act on each other. When the inductor current is coming down, voltage of the capacitor goes up. And then the voltage comes down and it goes back, so that's basically the power factor. This is the intriguing part that was on the shoulder. The energy basically keeps moving between the capacitor and the inductor. And of course, if you have a resistor, every time that it keeps moving back and forth, some of the energy is transferred to these. If the current goes through the resistor, it won't up. Right? You see out. So the energy comes out. And every round that the energy comes out, the magnitude of the voltage of the current starts coming down. That damping, that alpha.
See, here I have one capacitor and one inductor in parallel. I just set the initial voltage of this voltage. This capacitor for one. Let's see. What is going on here? We have a loss in. Sorry. What are these two fix? And they have a silver frequency, right? The same frequency, but different reason. Different. That's one of the fun. How can I change the frequency of these oscillations? Yeah, we change by but what's the relationship? If I ask you how much is the frequency of oscillation of this thing, tell me how much it is.
1.
Based on the relationship we had, we know how much is the oscillation frequency of anyone can tell. See. 1 over
1 over TG.
1 over
T.
no. Write it down.
Sixty.
Oh. We found the differential equation of this like this. We route one omega 3 at resonate or oscillation frequency and also as a damping factor. This one is the oscillation frequency omega 3. Now can you tell me how much is the oscillation frequency of music? 360 what?
That's
1 over, did you consider 2 pi? How much?
keep going for it. It goes.
5.33. And what's the unit? 50 hertz. Okay, let's see here. I can measure it here if you are. Okay. From here to here is 52 1.45. 1 over 1 point
1.4.
What's the initial?
One.
1.5. How each unit 2 milliseconds, 3 milliseconds. Each of from here. That 20 milliseconds, 1 over 20 milliseconds, almost
47 minutes.
I want to change the values and find 1 kilohertz. Anyone can tell me how much should be the value of the inductor?
What is
1 kilohertz. I want the frequency of oscillation to be 1 kilohertz.
Hmm.
Yeah. What's the relationship of oscillation frequency? 1 over radical gets here. You have capacitor, you have capacitor, you need to find inductor. So this is the oscillation frequency. Right. 2.5 milli. The oscillation frequency how much should be the period? 1 unity second. The frequency is 1 kilohertz. The period should be how much?
Sorry, 1/1 kilo.
Should be 1 millisecond. From here, 1, 3, 4, almost 5. And how much is like that in 200 microseconds? Multiply by 5 is 1 millisecond, which means your calculation was, yeah, that's 1 kilo. If I added a decimal here, what is gonna happen? Based on the equation, what we are doing here, I added a decimal here. What is changing in this equation? Do you think the oscillation frequency is changing? It's not gonna change. How about alpha? Which means we are changing damping factor.
When the damping factor is increased, what happens? It damps faster. When the damping factor is reduced, it takes longer. Next thing, we also look at it.
It is going to damp and shift to
And the dynamic is the same. It's the same kind of equation.
how can I omit this oscillation? How can I change the circuit going from under dam to critically dam or over dam? Which means I don't want to see this oscillation. What should I?
So what is overdamp? What is underdamp?
Under dam,
You over.
oscillation, we have a kind of oscillation before damping. Over dam, it's been directly goes down.
Zero.
Yeah, here, oh,
And what is damped? It's over and under. Is there a damp?
critically down.
What do they call it?
Critically down.
Critically damped.
Yeah, critically directly.
So, no matter how much I lecture you about, don't forget it. Some of the things you forget. So I have a question.
Can someone tell me how can I go from under them to over them? Which means I don't want to see this oscillation. I just want to be on damping vector. What should change here? What's the difference between under them and over them? You can find here based on the
Quality factor.
lesson
Quality.
quality factor. I haven't taught quality factor.
Good. Good, thank you. So can you teach us about the quality factor? Not you. Can you teach us about the quality factor?
It is omega over 2.
We'll teach for everyone as well. I like part of, part of the training is to also get you guys comfortable with explaining to others. I appreciate it. I love when people go ahead and please.
I don't know if it is right or not. If it is omega over alpha is bigger than omega.
Oh, yeah, true. We are talking about quality factor on LC tank. Yeah. And what does it mean?
If it is how we can go from overdamp to critically damp over.
Yeah, it's related to quality factor, but what does the quality factor mean by itself?
Quality factor.
What's the concept of quality factor of LC tank? We will reach to that after. Here we are looking for right now we are in underdamped situation. Yeah. We want to go to overdamp. What should we do? Yeah. We want to change this value. We can only change alpha and oscillation frequency. Yeah. Go from this situation to this situation. We know omega. Yeah. The oscillation frequency is 1 kilohertz. If I put alpha exactly equals to omega 3, which means I will go to critical. If I increase it a bit, exactly, I will come to omega. Your friend calculated and told us it should be 7.9. 7.9. Let's check. At first, I put in 10. I want to see if there is a change. There is a small relation. If I change it to 8. Change. This one doesn't have this. Relative value should be. It has a bit density, a bit. If I make it less. Almost it should come. Maybe already. I'm sure about that. So, how much? 31. Let me change one. If you to
Faster. Count down.
Now, it's
Coming to me. Tell me so that they can see the next number. So the damping it. Confidence. I don't, my eyes, I cannot see what.
patient. Quantity,
The one thing, how much?
or 6.5.
6.5.
One.
like 100 frequency at
150.
so that 1 kilohertz that you have, right, divided by 2 pi. You forgot to divide it by 2 pi. So you divide 1 kiloradian per second divided by 2 pi becomes the frequency, right? So at that frequency, how much is the impedance? You haven't taught the impedance yet, but what is the like the LC of it? L times C times sorry, it's not LC, L omega. What is L times omega is 1000, right?
Your station should be 100.
150 Hertz times 2 pi,
1K
1K. 1K times 100 nanohenry,
million.
100 millihenry. 1000 times 100 millihenry becomes 100. So basically, that's 100 ohm. Now the resistance that creates the critically damped is how much?
Don't get that. 50, I didn't calculate technical data.
There should be a ratio between these two that should be fixed.
Between, it depends to capacitor.
That's but the capacitor, when you have the resonance. Okay.
Related to capacitor and radio of the.
Okay. Sorry to interrupt you. Feel free to ask questions.
When okay, let's calculate together. How much is the resonance frequency?
1,000.
Yeah, that is 1/2 that's
I'm 16.
almost 1. So here we have the check frequency 1K. 1K right here. Okay. If we want to alpha b equal to right here. How much is alpha?
25 over 2.
1/2R. Okay. One over 2R, it should be equal to the alpha is 1/200. That we should have
1,000.
divided. Yes. Found it. For 50 ohm, it should go to critically. And then one, one K two, one K two. had here. We can have one damping response, something like that. Or almost doesn't matter. Or we can have under the depends on the voltage or current, it can change this waveform or this waveform. If we have two inductors or two capacitors in the circuit, they shouldn't be series or parallel. Yeah? If they are series or parallel, that means the circuit is first order. If we have two inductor or two capacitor, we never go to underdamped situation. We go to underdamped situation only if we have one inductor and one capacitor.
One, old one.
If we have one inductor or one capacitor, is it second order or first order? If you see first order behavior like that, actually, that means we need all two elements which can store the energy. Which means both of them should capacitor and here we have quality factor. The definition of quality factor is oscillation frequency over damping factor, which means how much energy can a RLC tank store, how much energy can RLC tank store. That's a kind of okay. So if in a circuit we have higher quality factor, which means they can hold the energy for a longer time. Yeah. That means the capability to save the store the energy more, which means the nothing sense. Yeah. We had different situation of RLC circuit. If we are over them, that means we have a big loss or small resistor that the circuit cannot store the energy. If we had a lossless circuit, which means we are storing all the energy we got at the beginning. Yeah. The bigger quality factor means we can store more. Up to now, we talked about zero input circuit, which means we didn't have any independent sources. If we have independent sources, what was the response? What is gonna be the response if I add an independent source?
Current so
I need to put the initial value to this. And that, yeah, it should be. I think any by fact, it doesn't matter for a second or the second. Previously, we had an initial condition which we could easily model it. You know, the capacitor with initial value of V0. We can consider it like that. It has an initial value, which means if we add an independent source, the behavior should be kind of like the initial condition. Again, if you write the equation, you will see it's exactly like before. If we solve again, we will have three different situations depending on damping factor and oscillation frequency. Do damping factor and oscillation frequency depend on input signal? They are only related to resistor, capacitor, and inductor. They don't depend on input signal. Input signals only show what is the beginning and how much is the final value of the voltage and current in the circuit. The result is exactly the same. If we suppose we have a arithmetic here, we want to find the differential equation related to IL. It should be easy for you to solve. How can we write a differential equation related to IL?
Use KB.
Yeah, we only know KVL and KVL. We should use KVL and KVL. The initial value, initial voltage of the capacitor is minus 2 volt, initial current of the inductor is 1 amp. If we write 1 kVA here, we have this equation, and in this equation, we all about IM, we can make a derivation, and that's the second order equation we have. And we learn how to solve. For initial condition, I need to apply KVL here. I can easily find the derivation of inductor current at the moment of T. We've got characteristic equation. If we solve that, we will have it has two real both, which means if it over them or under them. That's a Do we have oscillation here?
We have oscillation there.
There's no oscillation here.
Yes,
Yeah, exactly. Based on the code that's over. We don't have any oscillation. That kind of the empty waveform goes to zero. Okay, let's go to the exercise 15. In this circuit, we are looking to find resonance frequency and the relationship of voltage of the how technical anybody volunteer to help us to solve this one? Please you try to solve for yourself if you can or not.
see.
Eight, 10 to the power. Answer.
That's my that was do you think you need to write the equation by okay, let me give you a cheating. So if you find alpha and we have what are the S1 and 2? We have here S1, I think, O, I think, no?
It's like
No, that, you know, you wanted to know this.
Please.
You have alpha and you found it.
Alpha and
Yeah. You need to find this one. Depends on if this value is real. You need to write one of these. You don't need to solve this.
resistance.
50.
S1 and S2
You know,
minus
if you find the positive, which means you are doing wrong. That which means
minus
which if it's over them or under them.
Give me an error.
not error
Error, what do you mean?
Doesn't
minus.
Why?
It's giving an answer.
How much is alpha?
10 to the power 10.
10 to the power of 10. How much is
3.6.
yeah. If you subtract omega from alpha, then it should be negative. We can put it on true. Yeah. It's negative. Which means you have J.
So, all in one thing.
The J is equal for that.
One over. What is one over?
Error because it
What is J?
is
J
because it is
imaginary
imaginary particle. Not
Right.
imaginary.
radical minus 1.
Yeah, imaginary. Imaginary.
initial voltage of capacity. You are writing VAB, which is voltage of capacity. At the time of zero, it should be 1 volt. When you put T at zero, the result should be 1. You need another, what is that? Inch. We don't know what is gonna happen in this list that under. When we are solving a second order equation, we need 2 inch.
Okay, that's all.
Yeah. If you know, I am 0 is 0. You are writing BC, yeah, that's B. Here you write B. You need DB, you know. How can you find that value after? How much it is value? You should know that after that you move to make the derivation here and equal to difference. Make it equal to that. How much is derivation of voltage over time at the time of zero? We need to write a KVL here at the time of. Yeah. This one is IA. Can you write in the bottom? Yeah. If you write a KVL here, we have IL0, and you write IL0. How much is the current of capacity? We are looking for that. ddt over d plus C dV d over d. In which time? No, for V. For yeah. Yeah, exactly. I'm on plus this current. How much is this current? How much is this voltage?
It's 1.
Same as
Yes.
VC0 over
50. No,
50.
1 over 50.
right one.
But the voltage is on.
Right now, write VC0 after that. You will replace it, right? VC0 over 50 should be this. Okay. What do we have here? Do we know IL0?
Yes.
How much is IL0?
0.
How much is VC0?
This is 0 is 1.
1. We should replace VC0 by 1. And how much is C? The capacitor. Capacitance is 1 equals 1.
Then how much is IL? IL.
IR.
IL.
This is zero, yeah?
That's
We have zero. That MTP over. Now you need to make derivation. What's the derivation of e to the power of minus alpha 6? You can write complete derivation. So Which take yeah. It is bench formula alpha know how it's gonna the we found resonation frequency and the voltage of the voltage of the capacitor. Now they ask us what is the equivalent resistor from P and how do you find the equivalent resistor?
VAB over K.
What's the approach to find the equivalent resistor? When they give you a complicated circuit and ask you, okay, find the equivalent resistance of this circuit.
Down test of voltage.
Yeah. Since it has dependent sources, we need to apply voltages and currents, and we need to find the relationship between them. It is K B B. It is if I apply VT here, what is the relationship of IT and this current source?
It is the same but negative one.
They are the same or
Opposite direction.
opposite direction, which means IT is negative KBB. What is BCD?
BCD is 80.
Yes, exactly voltage of
VT.
this voltage. So VT is equal to VP. So IT minus KB are equaling VT over IT, which is minus K. What happened? If K is a positive value, we have a
Negative.
negative resistance. Can we have, do
It's
we
one
have
over
negative
K.
resistance?
1 over K, right? R equivalent.
Oh, yeah, thank you. 1 over minus 1 over K. Can we have negative resistance?
Yes.
Yes, we can. We can make it with electronic devices. So what's the point? You know, they ask us, we found there is a negative resistance here. Yeah. Why they want us to combine these two together to make it a loss circuit? That's what happened in real world. When you connect a capacitor and inductor together, because of parasitic resistances that capacitor and inductor have, you want to make one AC sources. You want it to continue last until end. But because of the internal resistance, after a while, it's gonna be like than a circuit. Yeah. Because these two have parameters. If I add one negative resistance here, what is the equivalent of these two? How much is the equivalent of two parallel resistance? One of them positive, another negative. If is zero, we just get multiply them, divide by zero. Infinity. That means it can be open circuit. Yeah, if it's open circuit, we have a lossless and it can continue that. Yeah.
We connected in series.
Exactly. We only need to connect this one to VA. If we connect that, which means I have this circuit can be a lossless circuit if what's the relationship between K and R? They should be, these two resistors should be same, yeah? If I want to have an infinity resistance, these two should be
The same.
same. What is the equivalent resistance of these dependent source? 1 over K. So 1 over K should be equal to R. How much is R? 50.
Minus.
In K should be 1 over 50.
Still look about the negative.
There's ones.
Minus.
Negative. Minus.
K shouldn't be negative here. If you put the K as a positive value, the equivalent resistance should be negative.
So we will remove the negative to.
You know, the absolute value should be.
Ah.
We know this. Okay. Negative. Yeah. If you put K minus 1 over 50, this equivalent resistance is positive. And that is let's try this. The I'm sure we can see those values here. Because oscillation frequency really. How much was the can?
One.
One pico. How much the reactive? 1 nano. So it's like that.
We see a pattern over there of two colors, one brighter, one lighter, and then it keeps, the media keeps going and shrinking. What's happening there? Why do we have two colors? Explain. Anybody can explain why we have two colors?
As we see. Voltage and
Sometimes my questions are done, don't worry. But the two plots are on top of each other, so it's actually two colors getting combined. Right?
I think
But even that one is an interesting physics. Yeah, it's basically constant, so it's got. And the slow pattern that is changing, what is what we call envelope. So you have the high frequency things, and then you have the low frequency thing that's on top of the application, you have one direction. But it's signal what it yeah. So basically say what is the maximum of it. That envelope is something that is you will also see in the simulator. So there are two kinds of fundamental simulation. One uses transient simulation, solving the differential equation. And the other way of solving is based on assuming that okay, every signal is the result of different harmonics. So it tries to solve for all the harmonics and put them together to generate a signal. That's called harmonic balance. And then in the simulators that use harmonic balance, there is features that are for simulating the envelope. And that's what we call envelope transient. So later, when we start working on the simulators in the RF, we will actually see those different names. But this envelope is something that is very important in all the modulations. Modulation are at the envelope. Sometimes at the envelope, sometimes at the base. Or something.
And with that, into this.
I'm looking for dependent current source. I found it earlier.
And he's finding. I'm basically trying to encourage you to keep remaining curious on anything. Anything that you see, ask for. Even the dumb question is better than no question. You know the answer of it. I grew up at the time that these computers, many of them didn't have graphics. Some of them then had it and they had to write assembly code to create the graphics. And for me, still it's fun to see that, oh, to actually see the two colors on the screen. So it was an exciting time for us in the 80s.
Was it one color?
But
Was it one color?
yeah, so basically some of the monitors only had the green and black at that some point. But when I started, I was using color monitor. I started graphics programming on Commodore 64, which used to be a very nice gaming tool as well. In fact, today you can go online and find multiple games of Commodore 64. There are sites that have all of them and you can play it. So for people like my generation, we can go to those sites and play all the games of our childhood, refresh our memories. But I am still young enough that I grew up video game. So a few minutes to the end of the session, I'd like you, for Dr. Hassan and myself, to spend a few minutes just memorizing your names and faces again, just to make sure that we practice to remember everyone. I'm starting to get better, but it takes a while to practice. That line. Last 100, one of it said, you get to memorize in fact. At the University of Tehran, I used to have a circus professor. He actually had a very interesting thing, but the class was very big company. But in 3 sessions, he was learning name of everything. And his technique was very simple. In the class, pick your chair, always sit there. So then, every time anybody was, at the beginning of the year, he was asking the name, was writing together after. Everybody was asking questions. So we did 2 or 3 days, he was acting as his genius, and then all the other thing. But by middle of the semester, you really were by name. Was each and every student department. But here, you have a people who cares that actually, but
Let's say it's
whatever. I used to be extremely excited to do the right stuff. I used to remember that I meet one guy once, 10 years later. Like, that's how that I know well of him. value. This is one of the nice features. If it works, you should see the signal growing. It does. It doesn't let you enter the gate.
But I many the dependent source as a negative.
So one of the projects that I was working as a consulting project was helping a simulation, new simulation that was being built, which is now part of ADS. They had some bugs in the programming. So the polarity of the current, so basically we say, okay, if the current is going in, that's the plus. Right? So if you change that, the voltage, the VI relationship, instead of V becoming RI, becomes minus RI, right? Just that mistake, the programmers had made it because they didn't know the circuits. And this simulator was always crashing, not converted. They had given us a complex circuit to run. Sometimes in the middle of the debugging, they had changed their polarity thing in the code. They didn't know that it's simple. And it was crashing. It took me 10 days to break down a complex circuit. And then because it was crashing, you couldn't see what's happening. So breaking it one by one, eliminating every piece, still crashing. Until I arrived and I realized that actually every resistor is accounted for as a negative resistor because of the wrong polarity. Was nice, but also damaging to my confidence in the simulation. So those bugs are there, not on some simplistic things. Like complex matters you see. That's why your foundation is always in. Be able to detect. Okay, so now we have the increasing costs.
Yeah, we have a negative resistance here. And we think if we can make sure both positive and negative resistance are equal to each other.
Now, one other intuitive question: if we could have a negative resistance and a positive, or we had a variable resistance that we could slowly change it between negative and positive, what would happen?
We can choose
Just equation. So we could start with a small signal, then going to negative, increasing the signal, and then going positive, reducing it as you are pushing the gas pedal or brake. Right? If you are negative, it starts increasing. So if you move to the negative, it starts becoming bigger. If you move it to zero, it becomes steady. Bring it to the positive, it starts going down. Right? So if you move it slowly, it's as if you are playing with your signal. So you could modulate your signal. Amplitude modulation. Which is, by the way, the concept of AM.
But for second order circuit. And then next session we will go for universal diversity circuit. Very low and we will see how we deal with that. If inputs are AP independent.
And that's the end of the class. Right?
I have that's the end of what I'm going.
What you are.
I have another slide that it should be said.
Then there is another very valuable document that Professor has prepared, which is about solving the complex node mesh problems using the matrix approach, using the matrices and solving it. So basically, that's the way the simulators are actually built and optimized. So if you actually look at SPICE, SPICE was built originally at UC Berkeley by the team of professors, a bunch of professors, including Professor Tesor and Professor Paul, who have written this famous book. electric circuits. And those kind of matrix methods are the core, the algorithms needed for solving those things, in addition to other numerical methods that we can. As circuit designer, we don't have time to do that. Right now, somebody wants to specialize in the simulator design things, but it's important that you also start self-study those by yourself. If you have questions, you will come to ask.
Mr. What is it called? What is it called?
What do we call?
Matrix?
Look at the material, you will see, you know it. You know
That's
something.
systematic approach of nodal and mesh analysis, which most of the software use this method to solve the
Yeah, I
complicated
think we
circuit.
saw the last question in the assignment. This. The last online,
No, there is no assignment on that.
no, I mean, we, in the assignment too, I had a question. The last question,
Yeah, yeah.
I think we solved it.
Yeah, usually software solve that with this method. Yeah. It had too many nodes and issues, it wasn't easy to.
Basically, if it's complex, you cannot think of it. It has to be automated.
Yeah, because I was saying, that goes round and round.
So computer has to do it using numerical methods, iterative methods, and fixed algorithms that will be repeated all the time. Computer cannot look at this and think that. Now it can. AI can. And because now it also makes mistakes.
It assigned
But
one
it is still
current
has
graph,
to be- that's it, I think.
and when it made the graph from circuit, start to make some matrix regarding the nodes and branches. So it doesn't matter what is inside the branches. At the first, it just simplifies the topology to this matrix. And these are the. After that, it goes inside each branch, find the relationship between voltages and current. Current and apply that to all the matrix. And it would be a systematic way of solving all complicated steps. You just look at these and see how we these complicated steps by solving these matrices. And we send these materials to the test.
It's nice to see how you can formalize the way that it's not about the way that you can simplify the machine.
Anyone solve fourth assignment?
I start, but I didn't.
You did it.
I started.
Oh, you just got that. Did you find it easy or not?
What?
Is it easy for you to solve or?
Easy.
Did you find it easy?
At the beginning it is easy. I don't know at the end it's easy.
Yeah.
So let us do the lesson for me and Dr. Hassan. Rememorize your names and your backgrounds. Are you okay, Hassan?
Sure.
Then they can do the exam on us later. So, can you tell us about yourself? What's your name? Wow. And you already have your accuracy. Right? From previous year.
But
And once you have 2 rounds, pass. What's the last one?